we were to make contact with aliens tomorrow, what language would we use to communicate? Hi, I'm Dr. Tom Crawford, and I'm here at the University of Oxford to talk about maths. Maths is often referred to as the language of the universe, and we've been sending mathematical signals into space for over 70 years. But how universal is it? Let's take possibly the most famous mathematical object, pi. As a mathematician, I might define pi as the distance around the edge of a circle divided by the distance across the circle passing through its center. If maths is truly the language of the universe, then it would be fair to expect us to be able to use it to describe pretty much anything. And the same goes for pi. Join me as I share with you some of my favorite alternative definitions of pi, which shine a light on the truly universal nature of maths as a language. Starting with football. When taking a penalty, the aim is to kick this football from 12 yards past a goalkeeper into the net behind me. Studies have shown that on average, a goalkeeper covers a semicircular area with a radius of 2.83 meters, which looks a little something like this. Therefore, when a player is taking a penalty, they should aim outside of this diving range. To allow for some error in the shot, we actually want to position a circle in the top corner of the goal because the center of this will be the equal distance from the goalkeeper, the crossbar at the top, and the post at the side. So the question becomes, how big is this circle? So let's start by drawing a diagram of our setup. This rectangle represents our goal. Then we can add the semicircle for the diving range of our goalkeeper. And we know this has a radius equal to 2.83 meters. We also know the height of a standard goal to be 2.44 meters, and half of the width is going to be 3.66. Now we want to fit a circle in this gap. I'm going to draw it in the left. It could also be in the right. And this has an unknown radius given by r. Now what we can actually do is form a triangle by joining up the two radii and then dropping this perpendicular to the bottom. So this gives us a right-angled triangle, which allows us to use Pythagoras' theorem. So that tells us the distance along the bottom squared plus the height squared has to be equal to the diagonal distance squared. If we now expand out this equation, we get approximately r squared minus 18r plus 11 is equal to 0. This is a quadratic equation which we solve using the quadratic formula, which tells us that r is 0.65 meters. So what we need is a circle of radius 0.65 meters. This is a circle of radius 0.65 meters. So all I have to do to maximize my chance of a successful penalty kick is hit the ball through this hoop. Easy, right? I'm actually a little nervous. Oh. Oh, no. Ah. Ooh. This is the one. Oh, I knocked the hoop out of place. This really shouldn't be that hard. This one. Yes! Oh! Win for maths right there. Straight through the hoop. Now we've seen me eventually hit the perfect penalty, you may be wondering what all of this has to do with pi. Now the area I was aiming for was of course a circle. And the area of a circle is equal to pi multiplied by the radius squared. So we can rearrange this expression to get the following. Pi is equal to the proportion of area for a perfect shot multiplied by the total area of the goal divided by twice the radius of the perfect placement circle squared. Our first alternative definition of pi. Next up, the Titanic and ping pong balls. Okay, so how many of these would it take to lift the Titanic from the ocean floor? A ping pong ball floats. This means its buoyancy force, the force acting upwards, is larger than its weight, which is the force pulling it down. Archimedes' principle tells us how to calculate the buoyancy force. It's equal to the weight of the fluid displaced by the object. So here, that means we need to know the volume of a ping pong ball, as well as the density of the Atlantic Ocean, because this is where the Titanic is situated. Once we have those two numbers, we can calculate the total buoyancy force of a single ping pong ball, and then we just have to work out how many we need to lift the whole ship. As before, we're going to start by drawing a diagram. So this is my ping pong ball, which has a standard weight equal to 2.7 grams, and we need to calculate the buoyancy force. Now this is equal to the volume of our ping pong ball. The volume of a sphere, which is of course the shape, is 4/3 pi times the radius cubed. The radius of a standard ping pong ball is 2 centimeters, so this gives us a volume of 33.5 centimeters cubed. Now, Archimedes' principle says we multiply this by the density of the Atlantic Ocean, which on average is 1.027 grams per centimeter cubed. So our total buoyancy force is equal to 34.4 grams. Now, subtracting the weight from the buoyancy tells us that a single ping pong ball can lift 31.7 grams. Now, the Titanic weighs a lot more than 31.7 grams. In fact, it weighs exactly 4.75 times 10 to the power 10 grams. So dividing this number by 31.7 gives us our final total of 1.498 billion ping pong balls. Now, unfortunately, I can't do this with the real ship for a whole host of reasons, not least because we don't have the budget. However, I do have this 3D printed model, this rather large tank of water. So, let's sink the Titanic, shall we? Here goes. The Titanic now lies at the bottom of the tank. Using the same approach as before that we did for the real ship, I've calculated that we need 11 ping pong balls to lift the 3D printed model. Now I just need a net to hold the balls. Ta-da! If my calculations are correct, this should float. Here goes nothing. Woo! Another win for maths. Now, not only have we raised the Titanic with ping pong balls, but you may have noticed earlier when we were calculating the buoyancy force that the number pi appeared in our calculation when working out the volume of a sphere. So, once again, we can rearrange the expression to get the following. Pi is equal to 3 times the weight of the Titanic divided by 4 times the number of ping pong balls required to lift the Titanic, times the density of the Atlantic Ocean, times the weight of a ping pong ball, times the radius of a ping pong ball cubed. Our second alternative definition of pi. For our final definition, I need to head to the kitchen. Let's go. Welcome to the Tom Rocks Maths Kitchen. Now, pi isn't just a number, it's also a tasty snack. So I'm going to be baking a pie-shaped cake using this fantastic dish. And not only is my cake going to be pie-shaped, all of the ingredients are also in multiples of pi. Let's do this. The only place to start is going to be with the appropriate attire. And then I believe, yep, the first ingredient is pie eggs. I can do 3. 1, 2, 3. All right, tricky part. 0.14 of an egg. There. That's very scientifically 0.14 of an egg. What's next? 63 pie grams, 200 grams of sugar, I think. Unfortunately, my scales don't work in multiples of pi. There we go. 63 pie grams of sugar. And I think I'm supposed to add this to the eggs. It's hard work. I'd say the eggs look sufficiently whipped, so let's get the oven up. So I don't have grease-proof paper, so I'm gonna go for butter. Same thing. Trickier than a normal baking tin. Sufficiently greased. Okay, 45 grams of flour. Going with 140. All right, baking powder. Teaspoon? About, small teaspoon? I'm going with that. Pie grams. Again, super accurate. I think these were supposed to be sieved, but it's gonna be a lumpy cake. My cooking skills are really coming to the fore here. I need butter, 14 pie grams. Okay, let's weigh this out first. This might be too much. Way too much. That'll do. So I do have a nice trick for melting butter. You do it in hot water. If cooking shows have taught me anything, you melt the butter in a bowl in hot water. Some excellent fluid dynamics going on in there. Starting to look like a cake. That's hot, that's hot, that's hot, that's hot. Okay, vanilla, 2 teaspoons, approximately. Oh. It's gonna be a very vanilla cake. We don't have to eat this. Come on, stuff cool. So now I am adding one set of liquids to the other set of liquids. Though I get to do it in a figure 8. I do like that. That's maths. Feels like a cake mixture. I think it's time to put it in the tin. Oh. Looks like a cake or a pie. Pie-shaped cake, pie-shaped cake. Right, let's put it in the oven. Look at that beauty. All right, time to decorate my cake. Okay, Nutella. You're not supposed to eat your own food, right? Final ingredient, whipped cream. Just look at that masterpiece. Not only have I baked a pie-shaped cake, but all of the ingredients are multiples of pi, making this our tastiest definition. Now, for our next definition of pi, I'm gonna need a chest book. All right, I guess we're just doing 3 definitions of pi, or more accurately, 3.14 definitions of pi. Thanks for watching.